Welcome back to Engineering Physics online lecture series. This is lecture number 2 on superconductivity. I am Dr. Raju SP, Assistant Professor in Physics, MC Hassan. So we will pull together a few contents related to superconductivity. In the very beginning, we will try to give brief introduction on it. And the second point that we will be covering in here will be on electrical resistivity on superconductivity, that is temperature dependency on it. And the third point will be on Meissner effect, how the magnetic field strength will influence or change the superconductivity state. And fourth point will be types of superconductors, type 1 and type 2 superconductors. And the fifth point will be the application part of the superconductors, particularly on maglev vehicles. Now, what are superconductors? Superconductors are materials that exhibit zero resistance at below certain temperature and expel magnetic lines of force or flux fields, and this phenomena is called as superconductivity. Suppose there is a material which will exhibit superconductivity, then if you need to bring down the temperature of the material below its critical temperature. If you do it, then what will happen? The material will start to offer zero resistance to the flow of electrons. And not only that, there will be expelling of magnetic lines of force. Suppose if you keep that material and you have maintained the temperature below its critical temperature, then the magnetic field that you are supplying will not be penetrating through that material. It will be completely expelled outside. Okay, and we'll come to that with great details. So now we'll head with basic definition of it. Supercurrent, the current which persists forever as long as the superconducting state is persisted in that material, is nothing but supercurrent. That is what the thing, the superconductivity, we have just discussed about it. And Camerlin Onnes, he is the gentleman who found out this property in the very beginning on this mercury. Okay, so he was just checking out by bringing down the temperature of materials, and he found out the offering made by the mercury, okay, below around 5 Kelvin, okay, to the flow of electrons, zero resistance to the flow of electrons. That happened abruptly after crossing that particular 4 to 5 Kelvin. The mercury started offering zero resistivity abruptly, not gradually, and that is the another point we need to make in here. So that is what the little bit background, and along with that, so this superconductivity has found out many applications in many advanced technologies around us, available around us. In the very beginning, quantum computers. So if you come across, you will come across with this in your future semesters. So quantum computers and maglev vehicles, MRI, that is magnetic resonance imaging, and magnetometry, that is to detect magnetic field, you can use it, and many more. Okay, let us talk about this superconductivity. Okay, and the two important parameters, that is, one is resistivity and another one is temperature. How varying temperature will vary the resistivity value. Okay, so for that, let us plot a graph, that is resistivity versus temperature. Now let us take an ordinary conductor. So by comparing, we can understand it more with the superconductors. Okay, so now let us take an ordinary good conductor and let us reduce the temperature of it. If you keep reducing, then the resistivity will also be lower and lower and lower. And now practically at this point, okay, we will end up with this point. So we expect, if you further reduce the temperature of it, we expect this curve has to go and touch this origin. Okay, so it has to go to zero. Resistivity should go to zero as you further decrease the temperature. Okay, so this is how we will expect, but this will not happen practically. If you do it, then what will happen? It will go and settle with some resistivity value, and let us call this as rho naught. Okay, because of some impurities present in that conductor, you cannot get rid of impurities in that material, so that is why you cannot get rid of the resistivity. Okay, so that is why there will be always non-zero resistivity for the flow of electrons. Okay, but if you consider a superconductor, and now if you bring down the temperature of it, then practically what will happen? So this will happen like this. So after crossing this particular point, it will not be gradual. Abruptly the temperature, the resistivity value will come back to 0. Okay, and this particular point of temperature axis will be called as critical temperature or transition temperature. Okay, so this is very important parameter to while defining the superconductors. So we'll look into the Meissner effect, the second important parameter or aspect related to superconductivity. So we'll look into. So now we'll look into it. What is this Meissner effect? Superconducting material expels magnetic lines of force completely out of the material within its superconducting state is nothing but Meissner effect. So now look into it. Let us look into it, how to understand this using a practical setup. So now let us consider this as a solid cylinder. This is a superconducting solid cylinder, and the temperature is kept above its critical temperature. So the temperature now, so let me just a minute. The temperature is just above the critical temperature, that is Tc. Now this solid cylinder wrapped around with primary and secondary coils. The secondary coil is connected to ballistic galvanometer and primary coil is connected to battery, and there is a plug key in here. So when the plug key is pressed, the primary coil is completed. So that is why, since it is connected to power supply, there is current in this primary coil, due to which there will be magnetic field produced around this coil, and that magnetic field will exert electrons flow in this secondary coil. Now it is happening, that is above the critical temperature. So soon after pressing this plug key, there will be deflection, but since the current is steady through this primary coil, even the ballistic galvanometer deflection will also get to a steady state. But now let us reduce the temperature of the entire setup or this superconducting material. But now if you cross the, now let us maintain the temperature below the critical temperature. Now if you maintain it, then what will happen? There will be suddenly there is a deflection in the ballistic galvanometer. So which implies, which indirectly tells us that this is due to Meissner effect. This is due to the expelling of magnetic lines of force from this material. So this is how it is on the left right side. So there is a superconducting material, and in below greater than this Tc, that is critical temperature, there will be magnetic lines of force penetrating through this material, but after crossing or after getting the temperature value below Tc, the material will start to expel magnetic lines of force. That is why there will be more magnetic lines of force present outside of this material. So that is why there will be more flux density outside of the body, and that is why there was some deflection in the ballistic galvanometer. Okay, so since there is no magnetic lines of force penetrating through this material, still the magnetic lines of force are present outside this material, the entire material will be lifted upside. Okay, so we'll come to this point because while explaining the maglev vehicles we need this. Okay, so this is something like n to n. The same effect can be found if you consider two magnetic materials and facing same poles opposite. Okay, if this is n and this is n, then if you bring these two magnetic material together, then what kind of effect that you will see, that is reflection, repulsion, that will be the effect that you can see even in here. But this is due to Meissner effect, that is simply opposition of n and n. Okay, so that is what the Meissner effect. And now let us try to understand the relation between critical magnetic field and critical temperature. So now we have got two important boundary conditions for the superconducting state of a superconductor. So maintaining simply critical temperature or temperature of the material below its critical temperature is not enough. You need to maintain even the magnetic field within the critical magnetic field. Okay, that is how it is. So let us consider magnetic field and temperature. Let us plot the graph between these two. Now to see the material exhibiting superconducting state, then you should maintain this. So this is critical temperature and this is critical magnetic field. So now if this is the critical temperature, you need to maintain the temperature of the material below Tc and below Hc. So suppose there is a material and you have applied Ns, that is magnetic field. You cannot simply exert, you cannot simply put this material in any strength of magnetic lines of force or magnetic field and see the expelling of magnetic lines of force outside this body. No, it will not happen. There will be some certain value of magnetic flux density until where you can see the material is expelling magnetic lines of force outside of this. So if you keep increasing the magnetic lines of force, so at particular point again there will be magnetic lines of force penetrating through this material. Okay, and that is the reason above this Hc. Okay, so this Hc and Tc are the boundary condition. Now if you further decrease the temperature below this Tc, you can see Hc is higher, which means what, you can slightly increase the magnetic field so that still the material is in its superconducting state. So it will be like this. Okay, if you further decrease the temperature, then there will be slightly higher in the value of Hc. So that is why it will be like this and like this. And if you maintain 0 Kelvin, there it will achieve some certain value, and let us call that value as H naught. H naught is the critical magnetic field at 0 Kelvin. Okay, if you decrease it, then if you decrease the temperature below and lower and lower, then Hc will be higher and higher. After crossing this, then it will be H naught, and it will happen even in this way. Okay, but Tc you need to maintain below Tc only. It will not be higher and higher. It is below Tc. Now let us have an equation, mathematical statement for this. So the relation between H naught, T and Tc. Tc is the critical temperature, H naught is the critical magnetic field at particular temperature. Okay, it might be this, this. So there will be Hc. But H naught is nothing but the critical magnetic field at T is equal to 0. T is the temperature that we are in or the material is kept, and Tc is the critical temperature. Okay, so that is what the relation. So Hc, H naught, T and Tc. Okay. Oh, we are here in the reflection zone. Let us have a quick quiz to make sure that we are on the right track in understanding about the superconductivity. The question, the multiple answer question is, superconductivity of a material appears. There are 4 options. You need to complete the statement. Superconductivity of a material appears above its critical temperature, below its critical temperature, at room temperature, none of the above. Okay, so pause it and think and answer. So now the answer is below its critical temperature. Superconductivity or superconducting state of a material will be present just below the critical temperature of that material. The fourth content is on types of superconductors. There are 2 types. One is type 1 and second one is type 2 superconductors. We'll take them up one by one. So let us take type 1 superconductors. To understand this, we need to plot graph between negative magnetization and magnetic field. Okay, this superconductivity is just the opposite of magnetization. You should not see magnetization of that superconducting material in order to call that or in order to see the superconducting state. So it is just the opposite. It is just the other way. Okay, there should be higher in the magnetization in negative direction, which means what, it should go towards the diamagnetism, which means what, there should not be any magnetic lines of force penetrating through that material, and that will be the what condition for this superconducting material or superconducting state. So now here this is minus m, okay, that is my negative magnetization versus magnetic field. If you increase the magnetic field, then there should be decrease in the magnetization, which means it should increase in the negative direction. Okay, so if you do that, then this would what would we get for type 1 superconductors. So as you increase the magnetic field strength, then there will be increase in the negative magnetization or demagnetization. But after crossing this Hc, we know what is this Hc. Hc is critical magnetic field below which the material will start to exhibit superconducting state, above which the material will simply turn into a normal material or normal conductor. Okay, so this is nothing but this type 1 superconductor. We need to notice one thing, that there is only one Hc, that is critical magnetic field. Okay, and this is the curve shape, and we need to keep it in our mind, and we need to compare this with type 2 superconductor to realize more about this type 1 and type 2 superconductors. So now about type 2 superconductors. Let us plot the same graph between type that is negative magnetization versus magnetic field. Okay, so this is negative magnetization and magnetic field. The shape of the curve will be like this. So from here, this point to this Hc1, the material is in type 1 type. Okay, the material is looking like type 1 superconductor, and here it is completely, there will not be any magnetic lines of force within that material. There are completely all magnetic lines of force being expelled out of this superconducting material until this Hc1. Okay, but after crossing this Hc1, if you further increase the magnetic field, then the curve will turn to right skewed curve, which means it will be slowly lower and lower and lower, which means what, there will be higher in magnetization, because this is negative magnetization direction, this will be positive magnetization direction. So this is, which means what, there will be partial flux or partial lines of force, magnetic lines of force penetrating through this material, through the superconducting material after crossing this Hc1. This is how it is. So let us consider superconductor, type 2 superconductor, and if you consider after crossing this Hc1, this is a mixed state, because this region where this is representing in yellow color, yellow color lines, these yellow color lines are called as normal conducting region. Okay, and these pink regions are vortex state or superconducting state. Here there are two states within the same material, that is superconducting state as well as normal conducting state or normal state of that material. Because of increment in the magnetic field strength, there will be partial flux magnetic lines of force penetrating through this material, and that is why there will be different regions present in this superconducting material. So here within this region there are number of magnetic lines of force where they are absent in this pink region. Okay, and this is called as vortex state. Okay, so and this is what the signature of this type 2 superconductor, and as you can see it in here, there are two Hc, that is Hc1 and Hc2. There are two critical magnetic field, and that is what the major difference between type 1 and type 2 superconductors. And this Hc and Hc1 and Hc2, the magnitude of difference will be very larger. If Hc1 is 1, then Hc2 will be in terms of hundreds. Okay, so that is why type 2 superconductors are practically very good, okay, for applications. So now the final thing, the end part of this lecture will be on maglev vehicles. Application of the superconductivity, of course, it has got tremendous, it has got number of applications, but we will be looking into maglev vehicles for the time being. So now maglev vehicles. So magnetic levitating vehicle is nothing but maglev vehicle. It is just the combined word from magnetic and levitating, these two, from these two words. The entire vehicle will be set afloat over the ground without touching the ground. This is a fantastic application of this superconductivity. We will look into it now. So let us consider, this is the aluminum guideway or the track of the uh, train. Okay, so you can find this train in Japan or China, and this is the fastest vehicle that you can see, okay, which will run over the ground, not just in the air. Of course, the flight or the air jets or the flight fighting jets speed will be higher, more than this, but on the ground this maglev vehicle will achieve the highest speed, and this will be the train. So here there will be two wheels where you can extract it and you can take it back inside this vehicle. Okay, so you can extract it and take it back whenever you want, and this will be the carriage where you can see the passengers sitting inside, and this will be the magnetic this will be the superconducting material. So this material will be simply coil. Okay, so this is just to this is used just to establish higher strength magnetic field, because this will be heavy. So that is why if you want to lift the entire train, you need to supply or establish higher magnetic flux density or higher magnetic field strength. So that is why this is the only possible way is to use the superconducting materials, and superconducting materials will produce higher magnetic field, and that is how this N and N will be produced. This is N, and the like poles will be repelling each other. So that is why the entire vehicle will be set afloat in the air. So that is why, because of there is no friction between this guideway or the track or rail with the train or the carriage, it can achieve highest speed. Okay, thank you. We'll get back to you on the next lecture video.